welcome. It's a pleasure to be here and to tell you a little bit about what we are doing, the topic. As I've heard, you have a very different backgrounds, so I try to be somehow not too specific, although in some points I have to be specific, but since we are a small group, you can always interrupt me as well if there are questions or if you would like to know something more, or just feel free to do that. What I will do is, in brief, I will give you a bit background of lake sediments and then mainly talk about methods, what we are doing. We developed some special methods also at GFZ, which I will present you here. And then I will take some time to introduce you into the concept of dwarf sediments. I will explain in a moment if you don't know what it is, what we mean with this. And then also have some time or use some time to talk about chronology, because if you do paleoclimate reconstructions, most people think about proxy data and climatic information in these sediments, but then forget about the chronology. So you must have a really precise and good chronology, and I will tell you what we understand about a precise chronology when we talk about dating lake sediments. And then I have at the end one example, one case study to show you maybe in one example what we can do with the methods that we are doing. Okay, just starting at a very broad point here, that is reconstructing climate is very important in the background of the IPCC discussion. So we are talking about human impact on climate change, but we really do not know about the natural fluctuations which already have been taken place since thousands or millions of years, and the mechanisms. So we would like to understand more about this, the climate system, how it works. And that's the reason why we go into natural archives, because when we talk about modeling into the future and only use the data what we have from instrumental observation, from temperature measurements, which are reaching back until, for example, 150 years, or in some places even a little bit longer. This covers only a very short time period of climatic fluctuations that we know. So it's not sufficient, and we have to go back in time. And as you can see here, there are many different ways in different environments where you can use natural archives for climatic information. And what you see here, I have taken only a selection of those, and you see these kind of laminations here. So there's kind of annual signal or seasonal signal in these archives, and that comes already to the point of these type of sediments, what I'm talking about, lake sediments. We are going into very high time resolution in our reconstruction. That's why we are focusing or looking at this kind of archives where you see here in the ice, you can have annual laminations. From trees, it's obvious, but in corals you have this, in speleothems, and in some of the lakes as well. So coming back in more general, so what is specific for lakes, why we are going into lakes? First of all, so there's a worldwide occurrence of lakes, so we can really compare different regions, different from, for example, ice cores, which are very known as very high resolution climatic archives, but which only tell us something about the Arctic and Antarctic regions. In lakes, you can go to all climatic zones and reconstruct regional climatic signals, which is very important for us. Another point is that we are in the terrestrial habitat. So we use the archives in the place where people are living. So that's where we actually are dealing with climatic change. And again, in the ice cores, for example, or if you are from the ocean, nobody's living there. It's important information to understand the climatic system, but for us, it's interesting or important to have this information from the region where we live. Another point is that we are dealing, or that we have continuous sedimentation, which is also important, that you have a continuous record of climatic change and not, for example, like river sediments or other types of sediments which are interrupted. I already talked about this point here, that is high resolution. So we are going really into detail. We are also trying to understand decadal scale climatic fluctuations, seasonal variability, rapid climate changes. Actually, what is rapid climate change? How fast can climate change from one state to another? That means we really have to go into very high resolution. That makes it a bit different from maybe general geological point of view, when you very often have long time scales, and it doesn't really matter if you have 1,000 years more or less. We are talking really here about 1 or 2 or 3 years, a few years more or less, and uncertainty. This is precise dating, and I will tell you more about this. And then another point which is very important when you talk about these lake sediments, I mean, the advantages that they are in the human habitat and that they have signals from the environment where we live. makes it that we have a kind of integrated signal. So there's climatic information, environmental information, and information about humans in lake. And humans is not only we in the industrialized civilization, we see signals of human disturbances, human interactions in lakes since many thousands of years already, during the whole Holocene actually. So this is some general point about lake sediments, and now I would like to come directly to these warped lake sediments or annually laminated sediments. That's what you see here. One example, I will explain you that a little bit more in detail. Here I would only like to say that with this you have actually two things at the same time. So you can do climate reconstruction at the seasonal scale when you look into detail in these laminations. We will do that in a few moments. And the second point is you can directly date these as well. So you can count these layers here like in tree rings, and then you have the proxy data and the dating from the same type of sediment at the same archive. So you don't have to use dating methods which imply just correlations and yeah. When you talk about annually laminated sediments, some people think, oh, that's very rare. Actually, it is. So if you look, for example, in Germany, we know probably about 20 lakes so far which have annual laminations. But if you look in the web, just Google warped lake sediments, you will see that there are many of these sediments available, especially in the regions where people have been working for decades on these kind of reconstructions in Europe, for example, but also in North America and Asia recently have been found. There's not so much information from regions like Africa and Southern America at the moment. Okay, so they are available, and I would like to give you now some background. So this is the reason why it's called warped. This is a warped lake sediment. This is a Swedish word. It comes from varviglera, and it means in Swedish layered clay. And it has been discovered by this man here. You see, 100 years ago, geologists were a little bit different dressed when they go into the field than we are today. This is Gérard Deyer, and he has seen this kind of sediments here. These were lake sediments, lake sediment outcrops, and these lakes existed in front of the glaciers at the end of the last glaciation when the glaciers moved or retreated in Scandinavia. So you had a lake which existed for maybe 100 or 200 years, and then it disappeared because the glacier was melting away. So what this man did, he found out, okay, this should be of annual rhythm because he has observed this, that there is a snow spring melt when all the material comes into the lake, and then you have a kind of graded deposit or grading here from silt to clay in the course of the year, and that is a rhythm which repeated year by year. So his idea was, okay, I just follow this type of lakes, do these measurements, measure the thickness of these layers, and then try to do a correlation from one of these lakes to the next, because they only existed for a very short time. I told you, 100 to 200 years. The ice melt was very fast. And then he did the correlation. This is how it looks like in core. So you could correlate from one lake sediment to the next. And by this, he was able to reconstruct the timing of the glacial retreat at the end of the last glaciation. So this was the first time in geology that an absolute age and absolute dating was achieved for something. Before it was only relative dating. This was the first time when you could have numbers in years, how many years did it take to melt back these ice. And actually there's still this so-called Swedish Warp chronology is still today used. It has been, of course, in the last 100 years several times corrected, but it's still in literature, and the Swedish people use that for their environmental reconstructions. So we are doing, and now it comes a bit more methodological again, what is our approach? So when we start with working on lake sediments, I told you one point is the proxy data. So that's the information we will get about climate, environment, and all the kind of information stored in these sediment archives. Like we can use sedimentology, we can have geochemistry, geophysics, but also a lot of biological parameters. I will tell you a few more in a moment. And at the same time, and that is really important, that you really should go for a precise dating at the same time. So there should be as much effort on investigating these records and dating as it is on proxy data. And altogether, this information is used to reconstruct then paleoclimate as a precise dating. And I will talk a little bit about this in more detail in the next minutes. But first, what is actually varved lake sediments? How is that defined? I say this because it's very often also in literature that people mix it up. When you see some kind of lamination, some people say, oh, this is a varved lake sediment. It is not, because there are all kinds of different types of mechanisms that can produce laminations, which are non-annual. So the first thing what you should do, or what you have to do when you work with these sediments, is that you have to prove that it's really a seasonal deposition. As de Geer did that 100 years ago, observing this, we still can do this today. We can use the actual observation to prove that we have really annual or seasonal sedimentation in these lakes. You can use depositional patterns. Once you have in one site defined or observed this, proved it, you can use the same type of sediment also in other sites, of course. You can use phenological information. You can go into the seasons, look for pollen, for example. If you see spring flowers, you know that this is the spring layer. And so there's very different ways. I only give you two examples here, how it looks like. One is taking sediment cores from lakes in consecutive years. This is a colleague of mine in Finland, and in Finland has a very typical type of varves. You will see these whitish layers and the dark layers here. The whitish layers are the spring snowmelt in present-day Finland, and the darkish is organic material, which is depositing in summer, and in winter the lakes are ice-covered, so there is a break in sedimentation here. So what you see here, that is a core taken in March 2003. So this is the so-called freeze core. You put a sediment, you put a sediment box or a box into the sediment and then freeze it in the lake in situ. And so the sediment is freezing on this metal piece. And what you see here, so this is the water. This is the sediment-water interface. The white is the frozen water, and this is the winter layer, because they take the samples in March from the ice short before the ice breakup. So what you can do then is you just go 1-2 years later, and you see the same type of, you see the same valves, and then you see, okay, here is the spring 2003, and here is directly following this core, and then they have the spring 2004, and this is the winter layer or summer layer 2005. So that's a proof that this is really annual laminations. You can do it in a different way. That's what we are doing here in our lakes, in our studies. You can use sediment traps, different types of traps. This trap, for example, here, you just keep it 1 month. Or this, you see, this is the whole sediment trap. This looks here at the bottom. You see this kind of revolver system, and so it turns around automatically every 2 weeks, and so it means that you get every 2 weeks a sedimentation here in this recorded in this sediment trap, and then you can use this information from the sediment traps, compare it with the sediments what you find in the core, and then you will find the rhythm of this typical layering, and then you have a proof of annual laminations. What do we need to have this kind of varved sediments? First of all, it's clear you need to have a kind of seasonal forcing for this sedimentation. At least 2, can be more, different types of sedimentation or sediment deposition per year. This is obvious. In all climates where you have seasonal climate, you will find this actually in all lakes. But why is it the case that you do not have these laminations preserved in most of the lakes? And this is because there are several factors which have to be fulfilled that this lamination is preserved. One is there should be no organisms living on the lake floor. That means the lake should be most of the year oxygen free, so must be anoxic conditions. Most of the year it can have 2 mixing periods with short oxygenation of the lake bottom, but in general there should be no organisms living there. Then there should be no wind-induced sediment mixing. That means the lake should be rather deep compared to its surface. So if you have large lakes, very often they do not contain annual laminations. Basically, it's really these kind of volcanic lakes, for example. They are small and very deep. And then you should have not too organic sediments, because then you have sediment degassing after a while, which disturbs also these laminations. So there are several factors which must be fulfilled to preserve annual laminations. And this is the case in few lakes, but it's also not continuously the case. You can even use, this is just one example, you can use this information about varves preserved and varves non-preserved as a climatic signal already. Here you see this is a transition from the Younger Dryas, so this is 11,600 years ago, beginning of the Holocene. And you see here in the late glacier, in the cold period, you have these laminations, maybe not so easy to see, but Here you have also varves, and here is a mixed sediment. So there was a period of about 50 years where there was a lot of quite stormy conditions where these sediments were not preserved. So you can use this signal as such. So I would like to go now a little bit more fundamental. So if you look at lake sediments at all, about the material, I told you at the beginning that there's an integrated signal, so you have a lot of different components in these sediments, and there are different ways to distinguish these components. The first, what you can do is you can distinguish the type of material. That is a very simple one, obvious one. So you have organic components, and these organic components can be allochthonous, so they can be washed in, or they can be autochthonous, they can be produced in the lake. This is already important because it's a different signal of this organic. One tells you something about the lake system, and the other one tells you something about the catchment of the lake. The same is with minerogenic or inorganic components. They can be either detrital, washed into the lake, or they can form autochthonously or endogenic in the lake. I will go into a bit more detail in a moment. So this is how to start to distinguish the type of lake sediments. And all this type of sediment keeps some kind or contains some kind of environmental or climatic information. Now you can do it in the other way, say, okay, what kind of information can I have in this lake? And then I can distinguish these type or can classify this into, first of all, catchment-derived materials. So what is the information about the catchment that I can get in lakes? And here you have biological information, for example, pollen, so you can reconstruct the vegetation, past vegetation in the catchment area. You have charcoal, which tells you something about burning, anthropogenic, so human-induced burning or natural burning. Plant macro remains, it's again something about vegetation, erosion. You have non-visible components which you do not see, which you can measure. There was one presentation here about biomarkers and leaf fluxes and isotopes on biomarkers which you can use. And you have minerogenic material, so this is washed in by snowmelt, for example, or flooding, river runoff. And this can be carbonates, siliciclastic material telling you something about erosion in the catchment. And erosion, again, can tell you something about human activity or natural conditions. Second information what you can have is about lake internal processes which are more directly related to climate. For example, algae, so that means what kind of organisms are living in the sediment, like diatoms, chrysophyte cysts, telling you something about water mixing, pH, nutrients, and so on. You have also minerogenic components which form in the lake. This is, for example, calcite, very typical in carbonate-rich catchments like in our region here. Aragonite, which is in arid regions, and probably in Argentina you will find this. Siderite, gypsum, so there are many different types. This is only just some examples. And then you have some lake internal processes which are not happening in the water column, but this is kind of reworking or which is forming into the sediments. So this is early diagenetic or post-sedimentary processes. Minerals, again, like vivianites and iron phosphide, sulfides are very common in lake sediments. They tell you something about early diagenetic processes and about the oxic conditions of the lake bottom. You can have material which is growing or living in the margins of the lake, which when this is reworked in the lake, that tells you something about wave activity, storminess, for example, like diatoms here, typical diatoms living on plant remains or carbonate concretions. So that tells you about all of this, what I just told you. And you can already see here now, and I just mark it for you, it is very difficult if you start to reconstruct climate because, for example, if you look at carbonates, some people do that, just measure the carbonate content in lake sediments, which is very easy to do. You will find many curves of carbonate contents in publications about lake sediments, but you can see here. So carbonates can be either from the catchment, can be washed in, they can be formed in the lake, or they can be just reworked from the shallow part of the lake. So this is very different mechanisms, very different processes. So that means you should know what kind of carbonates you have into the lake, and most commonly you even have mixed components which you should know about before starting interpretation of simple measurement proxies like, for example, organic carbon. Okay, so just to summarize this, if you do lake sediment or if you want to use lake sediments for paleoclimate reconstruction, you should use a so-called multi-proxy approach. I have shown you there are many components, and what you should do and what that's what we say proxy data. So proxy means we do not have really climatic, of course, there are no temperatures, but we get biological, chemical, sedimentological signals about climate in the past. So you should use as many as possible. It's like a mosaic. If you have only 2 or 3 proxies, it's just a very, it's a picture where you do not see very much. If you have many proxies, you have a full picture of what you can get. The point is that not all proxies are measurable in each sediment type, because if the sediment type is different, for example, in arid regions or in temperate climate or in tropics, then you have different types of sediment. I will show you in a moment. Then, of course, you cannot use all these proxies. And you should also know what kind of proxies are really important to measure in the sediment what you are going to study. Another point is if you do these reconstructions from this proxy data is the time resolution. That is only what you can only do, this kind of distinction in Warped Lake sediment. So this is an example here of a Warped Lake sediment. So what you commonly do, many people do, is you take centimeter bulk samples. So you just take a cubic centimeter or 2 from a lake sediment, and then you analyze it for pollen, for diatoms, whatever you like. And this, of course, includes a number of years, which is, it's an integral of certain time. That means it's so-called decadal scale type of sampling. But what you can also do is look at this year-by-year structure of composition of these sediments, and then you have this annual or seasonal signal, what I was talking about. And I would like now, because I already told you that depending where you are, you have very different types of sediment, I will just introduce you the main types, what we know. First is the so-called clastic varves, and the clastic varves are mainly formed in Arctic regions, so in cold regions, or in the high mountainous areas. That means these sediments basically consist of detrital mineralogenic matter. So the organic content is mostly less than 0.5%. This is a very classical type, proglacial varves, so varves forming lakes directly connected to glaciers. We observed this during the last glacial in regions where there was no glaciation, but there was permafrost or cold conditions, like here in central Germany, in volcanic lakes. It's the same type of mechanism. This is the snowmelt here, snowmelt in spring, and this is the clay layer formed in winter. And this is one example from a recent example from Svalbard, where you see the same type of signal. The problem is the proof of this annual character of this, if you don't have really a possibility of observation. And what you see here is kind of dropstone, and this is when you look into detail into this sediment, then you will find this. And these dropstones are deforming winter layers, so they just fall down in the after the ice melt up. And the size here, probably you don't see this, is 1 millimeter. So that's actually it's not a drop stone, it's a drop sand grain in this case. Then we have very common biogenic varves, which are forming in temperate climate zones, for example, in all over Europe or Asia, most of parts of Asia and China, you have this type of sediments. And there are 2 types of these sediments. One is if you are in non-carbonatic catchments, like for example volcanic lakes. This is from the Eifel region in western part of Germany. What you see here is so carbonate free, and the organic part is mainly made by diatoms that are siliceous algae. And you see different species here growing into different seasons. So this is actually this is chrysophyte cysts and no diatoms. These are only the diatoms here. This is early spring after ice breakup. This is summer. This is autumn. So you have this kind of succession, and then you know this annual rhythm. And if you are in carbonate-rich regions, like in the Alps, for example, or also in northern Germany, here in our region, you will find this very typical sedimentation here when you have in spring and early summer. That means during about 4 weeks in May, you have a calcite formation in the lake, and then you have in the rest of the year just some organic material stored here. Here you have an SEM picture. You see this is the organic material from actually from most of the year, from summer, autumn and winter, and then you have this bloom of calcite here, or this precipitation. It's a biochemical calcite precipitation, so it's originated by the algal bloom, but it's a chemical process then taking place in the lake. But keep in mind when I talk about annual or seasonal laminations here, so this is formed in 4 weeks and this is in the rest of the year. So this is actually, it's a simplification when you just say, okay, this is the summer season and the winter season. You have to look into a bit more detail. If you go into arid regions, like for example the Dead Sea, it becomes more complex, or here in Mongolia. Then you have in summer, mostly in the hot season, you have evaporation and then you have aragonite formation. This is aragonite layers, and then in the colder season, the winter season, you have runoff mostly from the catchment because there is not much vegetation there. That means clastic detrital material here. This is a very typical succession. In the Dead Sea, it's more complicated because if in especially dry years, you even have a season with gypsum precipitation, which does not take place every year. And there are many more types of these vats, which I'm not going into more detail, mixed types, depending on climatic changes. Actually, this is already the first information about climate, what you get when you look into these sediments. And now I will tell you a little bit about how we get this information, just basically what is the methodological approach. So this starts here with the coring. And coring means in this case, and I'm not saying drilling, and I'm not saying drilling on purpose, because it's not like in industry where you use rotating drilling, because you can imagine, and I haven't said that yet, these laminations are very fine, very thin, so they are often much less than a millimeter, so between 0.2 millimeter and probably 3-4 millimeters. And if you would use this kind of rotating drilling, then you would disturb the lamination. So what we do is we really cut this out, we hammer the sediment. It's very specific or very specific types of coring systems, piston coring system have been developed. Or what you use, and that's what I told you before, this is a freeze core here. You see this kind of metal bit. This is just penetrated into the ground, and then you freeze it with a mixture of liquid nitrogen and alcohol, which is minus 90 degrees. Keep it for 1 hour in the lake bottom, and then the sediment freezes here, and you can take it out in situ. What you see actually here is from an example in Switzerland. This is not climatic change. This is the onset of agriculture in the region nearby this lake. Next step is what you have to do is you have to prepare samples for microscope analysis. So this is actually classical geological analysis, petrographic microscope. But the preparation of the material is quite complicated. So you have to cut out from the sediment cores. This is wet mud. You have to shock freeze it here, and then you have to impregnate it into resin so that you can really use it or can treat it as a kind of rock. Then you have to polish it and prepare a thin section. And the thin sections here, normally what we are using are 10 centimeters long, so they're different scale and normal or petrographic thin sections, what we are going to use here. And these kind of thin sections then are used to investigate this record. And actually this happens for very long records like you see here. Basic principle already in coring, and this is an example here, 15 meters. So what you do always, you have an overlapping coring, and then you do this correlation based on sometimes macroscopic, sometimes microscopic, visible clearly marker layers here, because you need a continuous profile, so there should not be any kind of gap in there. And when I mean gap, I don't talk about maybe 10 centimeter, whatever. I really mean there shouldn't be a gap of even 10 years. So we really want to have a complete sequence. And that also means that from the whole sequence here, that is a so-called composite profile, we prepare overlapping thin sections. So this is overlapping coring for getting the whole thing, and then you do this overlapping thin section. So there's always 2 centimeters overlap between one thin section. This is schematic drawing here. And there are always layers which you normally or often do not see macroscopically, but in thin sections you can distinguish them. Either it's just marker layers or it's a sequence of layers, whatever, which you can really put then together. And with you, this is just one simple example where you can directly see this. I mean, it's easy to do this kind of correlation. But you do that really step by step for 10 meters of sediment to get a complete profile of thin sections. Okay, this is just one more image how that looks like and the impregnation. Next step is that you then use this petrographic, and can be short with this probably, methods. Only give you one example. You use different light conditions. This is one valve here in one of the lake sediments, and what you see here is this is the boundary between, this is the winter clay layer here, and then you have what you do not see in plane parallel later. It just looks light, but here you can see these light dots. This is calcite, so this is the spring calcite precipitation. Then you have here what looks dark here, and here is a bit light. This is organic material, which is hard to identify, at least here in the microscope you can see that. And then you have a kind of mixed layer here, you see here, and this blue, probably it's not easy to see, but these blue minerals are vivianite, so iron phosphide, which is formed in the lake. This is organic material which has been washed in the autumn, and in this organic layers you typically have early diagenetic vivianite formation here. And then you have what you can see here, this dark or this brownish color. This is the winter clay. So that is how we work on this. And what do we learn from this? I mean, this is just, I mean, what we say is this kind of, this is the anatomy of Mars. What does it tell us for us? For example, just go shortly through this. Here you see one example. This is a lake sediment from the last interglacial. This is 130,000 years old. And what you see here is, sometimes you see these are organic remains, and here is iron sulfide. So this is early diagenetic iron sulfide formation, or it's decomposition actually of organic material. And if you, for example, then go and just measure iron content in the lake, you will have here very high peak in iron, and people can start to interpret it in many different ways. But if you know how that is formed, that helps you to interpret this sediment. What you see here, I mean, this is the dropstone. I already told you about this. These are two different things here. This is just one event. You see that it already looks different. It's a 1 millimeter, but this is an indication for a flood event, what happened in that time here. And this darkish material here is a volcanic eruption. So sometimes you have tephra layers, volcanic material, visible or non-visible in these lake sediments. And here you can even say, okay, this is 130,000 years, but this volcanic eruption happened in summer, because this is the calcite formation which happens or which occurs in May. So you can even date, or you can reconstruct the seasonality of these kind of events. Another example, if you have a sediment like this type here, and then you see, oh, there's a color change. Why is that color change in the sediment? What does it mean? Does it tell me something about the environment? And if you do that, and I'm just going now into the transition here, and this is the set of thin sections enlarged, you will see that this type of layers suddenly started to appear at this position here. There's a first one here, or a first one here probably, and then they are regularly occurring here, and yet they're not happening here. So these are typical snowmelt layers, and there's a shift in the environment from a system which do not have snowmelt layers to a system which had snowmelt layers. So that's a way, just some examples how to explain sedimentation processes and relate it to climatic changes. Okay, I probably can skip this. This is just another example for this. Yeah, just maybe keep this for a moment. So just to distinguish between, to understand signals coming from or material coming from the catchment or something what formed in the lake. This is an example from the Dead Sea here. What you see here is gypsum crystals which are formed in the lake, so in the sediment. So they're early diagenetic gypsum crystals. You can distinguish this from gypsum which forms in the water column and settles down. So this looks much different. The same is here. This is very important, was very important for us. It's hard to see. This is growth of secondary greigite. This is also an iron sulfide. And this is important for the people doing paleomag work, because this gives a very strange signal in paleomagnetic records. Okay, and again, why is it important to have a look at the sediments and to use the sediment information in addition to these bulk sediments? This is an example here. Again, this is from the transition from the last interglacial into the glacial, example from southern Italy. And what you see here, these are 1 centimeter samples. So, and you do not see, I mean, this is on a thin section. You can see that there are differences in sediments. But if you take the samples, people normally do not consider this, and they're not so obvious as you see them here. It's just some color changes, and people just, just take the sample centimeter by centimeter. And this is a real example. So we had this is from a project a couple of years ago. And then they came up with a reconstruction of very simple parameter, only the tree pollen in this record. And what you see here is tree pollen more than 90%, so there was fully vegetated catchment. That was an interglacial sediment, so that was the last interglacial. The timing here is around 110,000 years. And then you go into the glacial situation with much less vegetation cover here, but you see these fluctuations here. And so there was an interpretation, and we had about half a year a very heavy discussions about the meaning of this kind of peaks, and people said, okay, at the end of the interglacial we had very high or strong climatic fluctuations. But later, I mean, it was very easy to see if you went back into this information here, and it's just a bit more in detail. What you see here is all the samples which has been taken from these layers here. They gave these signals of high tree pollen. And this was just reworked material, because at the climatic situation would change here, the lake level dropped. And when the lake level dropped, you had the old lake sediment in the littoral that was just washed into the lake by storms. And these are these kind of signals what you have. So this is just the process of lake level lowering, and actually the shift from vegetated to non-vegetated was much sharper and without any kind of these fluctuations. So this is another reason why we should use this kind of information. I will probably skip this. This is just unknown. This is another point what you should consider. So conventionally, people take these 1 centimeter samples from the sediments. That if you don't have laminations, you actually have to do this. But what we can do, if you have these sediments, you can just change it and have a selection or subsampling concerning time. So you can say, okay, I take samples with 5 years intervals, I can take samples with 2 years, including only, or I can take maybe even just single years, which is very laborious, of course. But so you have an idea how many years, how much time is integrated in your sample, what you take, what you have taken. Okay, and then there's another step in the method. So that was one part, that was the microphages analysis, that was the reconstruction of the sediment type. Mostly this is non-quantitative. You have a qualitative information, which is important, but it's you don't have a quantification. So what we do now is we combine this method with micro XRF scanning, that is X-ray fluorescence measurements, and we do that on the same material. So this is a thin section made from this sediment block, and then you can measure here at a very high resolution the chemical composition of the major elements with this machine here. And what you see here, these are the sediment blocks. You define a line of measurements, and you measure then in, these are the measurement spots. This is spot size is 50 microns, so you have a 50 micron resolution, and you can measure over the whole length of these thin sections, which means that, for example, if you have a thickness of an annual lamination of 500 or half a millimeter, you have 10 measurements for 1 year in the past. So this is extreme high resolution, and I show you some examples how that looks like. This is, for example, the calcium counts here in blue that show you this is the spring, or the spring calcite precipitation in the lake, and these silica counts, this is the winter layer. And here you can see a comparison between different resolutions. When you measure at different resolutions, here you get the annual signal, and here you, with 500 microns, you have more or less lost this signal. Some more example of this is how to use this method to distinguish complicated sediment types. This is from the Dead Sea, and I told you there's a very complicated mixture of detrital material, as carbonatic material, of gypsum, of aragonite precipitation, and each of these layers telling a different story. And here you can see how you can easily distinguish between those. So the blue line, if you see here, is calcite, and all the time when the blue line here is going together with the red line, which is strontium, then you know that is aragonite. If your blue line, the calcium line, goes together with the sulfur line, you know, okay, this is gypsum. You check this in the microscope, and once you have done it, you can always use this information for long sequences of sediments. So this is how you can combine this kind of quantitative or semi-quantitative information, elemental composition, and facies information. Okay, so what you can do here, this is the example what you have seen at the beginning. This is again studying rapid climatic changes. One example I will show you in a moment in a little bit more detail. This is from the warm phase in the late glacial interstadial, so-called Alleröd. Time here is 12,700 years. And you see here a very different type of sediment than here. And this is a large climatic change here. And these are the measurements of iron. The iron is representing the siderite. These light layers are siderite layers here. So you can see that is so the decrease in siderite here. Actually, the iron here means something different. So that shows in phases and in element composition a rapid climatic change. As I say, I'll show you in a moment again. You can play with this even a little bit more. You can produce 3D images. What you see again here is this is only, you see, it's 1 millimeter. So you see here, this is all of these lines here is one year or one spring precipitation of calcite. Here is used iron as a signal for the winter layer. And what you can even see here, this is one of the so-called drop stones or drop sand grains. It's a dolomite. This is an alpine region here. And what you can even see here, these are some very fine layers of dolomite produced by wash-in or small floods here. And you can even see that this, so here's top, here's bottom, that this is deforming, so that when this moved into the sediment, it was deforming one of these layers. So it's really detailed information about the sediment. Okay, I can skip this. And I will say a few words now about chronology. I told you that chronology is an important point, and so there are very different ways to construct chronologies in lake sediments, and I'm choosing this WAF chronology here, and I will tell you a little bit more about this. And if you find this in books, you often says it goes back 10,000 years, but of course you can, okay, it's maybe marked also here, you can do that for much longer times. And how is that done? No, before I say how is it done, I will tell you what you can get out of this. This type of dating is able to produce, first of all, information about the absolute ages. So if you produce a chronology by WAF counting, you can say, oh, this change here happened at 11,600 years ago. But what is for us, even for understanding, even more important, because this of course has a certain error here, you can clearly identify lengths of certain periods of change. You can say, okay, this is 1,090 years period of a specific climate. This is the Younger Dryas here. Or this is only 140 years. So you can say something about the length of climatic periods. And this is, the next point is, then you can also say transitions. How long is the transition? From one state to the next, does it take hundreds of years, thousands of years, or only 10 years? In this case, it's maybe 10 to 15 years. So you can be very precise in this kind of rapid climatic changes. I will show you just some examples how that works now. What are the sources of uncertainty? Like each dating method, there are also uncertainties in WAF dating. If there's poor WAF quality, if there are some intervals are non-WAFed, I told you, that is not always continuously, or if there's single or groups of WAFs missing by erosion. I will give you a few examples to show you, just to give you an impression. All this what you see here is scans of thin sections. It's the same sediment, one core taken in 2009, the other one a couple of years before. What you see here in the old core, there's some mixed interval, which of course, if you don't have this information, you do not know what to do. So commonly you do some interpolation, you count the number of years here, you count the here, and then you calculate the mean thickness of those, and that is what you use for interpolating the time in this interval. In this case, we could check it, our interpolation, which was really good, because you see that is have been found in this new core in a bit better way. You can have the same thing. So this is also two sediment cores. They are just in a distance from 150 meters. And you see here some interval, it's kind of mixed interval, which is not in this core. So you could actually do the same thing. You could say, okay, I just interpolated here, use the thickness of the WAFs here, and then I have the time in that. But the comparison of this revealed very clearly, because all these are, this is defined in the microscope, of course. that these layers are the same, that this part here is kind of mixed sediment. So that was just additionally brought into the lake by kind of reworking, telling you that there's actually no time in this. So if you would interpolate here, you would do kind of mistake into the chronology. So that also tells you something about sedimentation processes actually. Or you have, like in this case, missing years here because of you can see this. If you only have this, you would not recognize it that there's something missing, but if you do the comparison with an old core, you can see that. So constructing chronologies, if you're going to do that, is you have multiple cores to compare different cores from different parts of the basin. You have to do multiple counting just to estimate an error here. And another point is what I forgot to say at the end. This is only one part of the dating, like with the multi-proxy approach. You should also use other dating techniques like radiocarbon or cesium dating, at least 2 different dating techniques to independent dating techniques to prove each other or to test each other, these methods. Okay, this is just one example. What we did is counting different cores and just trying to estimate how many single varves are missing in cores. And if you do that for 10,000 years, it has been done here for 10,000 years on 3 cores, that it shows that in single cores up to 1% may be missing. Oops, that was the wrong direction. Okay, and this is another set, this is what I told you, to combine different methods. This is radiocarbon dating. This is the radiocarbon calibration curve here, the black line, and the blue dots. These are radiocarbon dates taken from this sediment core which we were dating here, based on the, so comparing the radiocarbon dating here with the calendar years, and calendar years in this case were varve counted. And then we had additionally 2 tephra layers, volcanic eruptions here, which are isochronous time markers, which you can see fit very well in our chronological approach here. So with these 3 methods, we were quite sure that we have a good chronology here with 1% error. So that means really when we talk about 10,000 years, we have an error of maximum 100 years in dating. Okay, and now at the end I will come to one example, and this is from this Maar Lake here in the Eifel. That's where we have been working since 20 years now. Just how it looks like. So you see, oops, you can see here the Maar crater, which is much bigger than the present day lake. And you see here kind of a village which has been, well, which is in this crater and some agricultural land. And then you would see just from an airplane, you see here this little white dot. This is our coring platform. Coring platform, oops, from a bit closer, that is here, and now we are in the crater. You look at this village here, and this is just an image from the crater rim in the winter situation when the lake is frozen. So what I want to show you here is just one interval which we have been studying in very great detail. This is a record here from Greenland ice cores. That's also what you have to do, compare with other regions. What we see here, 11,500 years ago. So this is the last big climatic fluctuation of the last glaciation. So the so-called Younger Dryas, it's around 1100 years, cold period, and since that time it never had been such a big climatic fluctuation. So this is the variability of climate is much less. If you go in the lake, compared with the lake sediment, again a very simple proxy here. This is the tree pollen only. You will see here it's most of the time is more or less 100%, so there's completely vegetated catchment around the lake. You see that there's here some changes. Here is this cold period. The isotopes here indicate in Greenland. What we see here is that the vegetation was different here, and that the tree vegetation could not survive, at least not largely. This is human impact here. Yeah? This is not natural, and you see it already started here almost 4,000 years ago in this region. But I would like to show you a little bit more now, or to focus on this time when that was the last cooling what we had. So the beginning of this cold interval, which we wanted to look into more detail. What happened? How long? How is it expressed in the lake, and how long did it take? Again, so this is this cold period in vegetation. So this is the decrease in tree pollen. This is the time here, time scale, to have 1,700 around here. This is a valve thickness curve measuring the thickness of the valves. You can see here is a big shift, and at the beginning here of this period, and that's what we are looking now into more detail. What happened here? Why is this shift? What is change happening? Actually, this is here a reworking material after a volcanic eruption, which is a time marker for us. So now we are looking, and you have seen that actually before in the slide, just into more detail now. So we are now going here into this period of very thin valves, less than 0.5 millimeter thick. This is typical thin section image from cross-polarized light. This is siderite formation here. That tells us something, that there was a rather deep lake, very anoxic conditions, very little water movement. So it was a very stable condition, but it was also not very productive lake at that time. And then moving into this thick valves here, you see completely different. This is more or less the same scale here. You see one valve is here even, it's more than a millimeter, up to 2 or 3 millimeters even. You see it's very high interannual fluctuations also. And what happened here, the siderite is completely gone. That means there was much less oxic conditions. What you see here is in this autumn winter layer, there's a lot of material. You see these thick diatoms here. This is epiphytic diatoms, so this material washed from the littoral zone. So there was a lot of wave activity bringing this material and nutrients from this material into the lake. And then this here, which you actually would not expect in cold conditions, is a layer of pure diatoms. So there was a very high productive lake at that time. And the productivity occurred because there was additional nutrients from the reworking of the catchment and because of the mixing of the water. So nutrients stored into the lake when it was very stable and anoxic in this period now became remobilized and allowed these diatoms to bloom for a couple of 100 years. So this is what we have observed. And then what you can do is you can just count, and this is just the years here. It's BP means before present. And then you can say, okay, the transition, this is a transitional zone, that is 10 to 15 years. So this change happened extremely quickly. That happened in time dimensions, which are the people, hunters and gatherers living in that area, of course, have really realized that within one generation, a big change. And temperature reconstructions, regional temperature reconstructions tell us that there were a change of 4 degrees, a decrease of 4 degrees temperatures in this short period. Okay, I will probably skip this summary here, or maybe just go through this. So, Barfed lake sediments are really valuable archives to do, especially these very high resolution reconstructions, because we have independent timescales. Microphases is important information. What we use these kind of methods to understand the sediment or the sedimentary system for interpretation of proxy data. And it is, if you want to do a reliable or robust reconstruction, you always need to do, and that's quite laborious and time-consuming, multi-proxies, so many proxies and multiple dating, more than what I have shown you here. That was just a short example. Okay, and at the very end, and that was with the help of Juan, he just put that together for me, just starting to look at Argentina. What do we know about Argentina, about lake sediments? They were the most famous project here is in the southern part. This is Laguna Potok-Eike. There was an ICDP coring. The last 16,000 years were recovered here. And this is then, oh no, I took this out. Okay, another type of lake. What is also common in Argentina is glacial lakes in the Andes here. And what you see here, there's one paper in 2011. You can already see this here. So these are clastic valves which have been formed here, and we have only the top core, the last few hundred years, which are recovered here. And then coming to the region, oh no, this is from the proglacial lake. It's 400 years. Now this is a very typical so-called multi-proxy data series. What you see here is that they have clay minerals. You see that the decreased water content is increasing. Then you have these micro XRF measurements, valve thickness measurements, and so on. So you put all this data together at the end. And then we come to one of these lakes which are in the region which we are now focusing on and which we will probably have a look. This is this Laguna Pozuelos. There was a some studies have been done, and you see here different types of facies distinguished, and here you have a lot of evaporatic sedimentation also in these lakes, and this is something what Johan will do, and we are going to look for a good lake in this region. Okay, this is just something what has been published there. I'm not going into detail here. Yeah, that's what you can do. Finally, with this, if you want to come from, say, climatic reconstruction to kind of landscape reconstruction about the change of this type of lakes, especially in these more arid or semi-arid regions, you have a change from large lakes to smaller lakes over time, or even to partly dried out lakes. This is the type of thing what we are hoping to do at the end of this project. And I would like to thank you with some images of lake coring, what we did in the different sites. Okay, thank you very much, and I'm open for questions.